So, in this video, I want to really focus on what happens when you start doing what's called a phase shift, right? Shifting things left and right, and that really is determined by when you add or subtract something that's within this x value, within the sine function, within the cosine, not outside it. And so, I think E is a great example that when you see the +2 here, that happens after the function. So that's a shift up 2 units. But when it's inside, it's a shift left and right, just like quadratics, right? So when you think about a quadratic function like y equals x minus 7 squared plus 5, the plus 5, that's a shift up 5 units, where the minus 7 is actually a shift to the right 7 units. Now, what you want to be careful of, though, is if there's a coefficient in front of your x first, you want to factor that out. And so, it'd be very similar if you had like y equals 2x squared plus 5x plus 6, and you wanted to complete the square, one of my favorite things to do, you'd want to factor that 2 out first. So that's what I'm going to do for example D here. And this is still problem set 1. So I know it's a sine function. I know this 6 is going to stretch it for its amplitude, but I'm also going to think about, sorry, I got the pen here. I want to think about that 4, so y equals 6 sine. I'm going to do sort of like a big bracket, 4, and then x minus something. And I want to think about, well, what would have gone there once I distribute that 4, and if I divide out that 4, that's really minus pi over 8. And again, you can kind of check your work just to double check to say, okay, well, 4 times pi over 8, oh yeah, that would have been pi over 2. Or pi over 2 divided by 4, yep, that's 8. So what that pi over 8, that really is going to shift things to the right, pi over 8. But I would recommend do your shifting last. So figure out what is the markings, what the graph would look like, and then take that and you would shift it to the right by pi 8 units. So kind of ignore that for a second. Kind of just think about y equals 6 sine of just the 4x part, just for now. Again, we said that's an amplitude of 6. The new period, so 2 pi divided by 4, right? Because sine and cosine, secant and cosecant, it's 2 pi divided by 4. So our new period is pi over 2. So I'm going to draw a sine function, a sine wave that has an amplitude of 6 and a fundamental period of pi over 2. And again, labeling last, I think is smart. So we can draw our sine, maybe a nice green. Oh, thought I picked green. There we go. So a sine wave starts at the 0, 0, goes up to the top, comes down, comes back up. And then same thing down here, down and back up. So that's, I'm going to call that highest point 6, this lowest point -6. And then remember we said we need a fundamental length of pi over 2. And so then we divide that into 4 quadrants. And so, again, dividing pi over 2 by 4 means that, oh, look at that. There's that number again, pi 8ths. Each of these tick marks will be a pi 8ths. And that's sort of like nice because our shift is about an increment of pi 8ths. That's pi 8ths, 2 pi 8ths. If you wanted to leave it as 2 pi 8ths, you could. I don't care. There's 3 pi 8ths. And here's 4 pi 8ths, which we know as pi over 2. So there's the negative pi over 2. Negative 3 pi over 8. Then there's negative pi over 4, which is 2 pi, or pi over 2, or no, which is 2 pi over 8. Wow, I can't even think this morning. And then negative pi over 8. So that would be perfect if it was just the sine of 6 sine of 4x. But now we need to shift that to the right pi over 8 units. So I mean, one thing I can do, not fair for you guys, but if I were to have traced this out, this image, it would be really easy for me to say, okay, now just shift that to the right, pi over 8 units. So it's going to look like a negative cosine graph, right? Because it's going to be starting down there. And that's okay. Like, it's okay that this is not symmetric. Like, it's okay there's more of the graph to the right than the left. That is perfectly fine. So, but since you guys can't do that, well, here's how I would suggest to graph that. Go, instead of starting at the origin, I guess I'll go to this, I start this bright blue. So instead of starting the origin, it starts to the right, pi over 8 units. And then instead of the peak being here, it's over to the right, pi over 8 units. Instead of this intercept being here, it's over pi, right? Instead of the lowest part being here, it's over pi over 8. And then there's another spot over here, that's pi over 8. So if you sort of just shift the anchor points, you can get a nice graph that's shifted to the right, pi over 8. And it's okay that it went beyond that. I don't care. So then the lower point would be here, the center point, the upper point, and the lower point. And you don't have to go there, right? Because you already got your 2 fundamental periods. So then the blue graph is the final answer. Now, somehow you might need to distinguish that for me. So you might want to label it, use different colors, call that the final graph. Somehow distinguish that the blue answer is the right one. Or sometimes if you're doing this in pencil, like students like to make some of the other ones dashed, right? So we can tell, oh, it's like sort of just part of the graph, but leave it because it's part of your work, right? But it's part of your work. Okay, so let's look at then, maybe what I'm going to do is I'm going to jump down to problem set number 2, and I want to look at, I thought there was one that was here, but I guess not. So never mind. We'll stick we'll stick on problem set 1. Let's do -2 cosine of 1/2 x plus pi plus 2. And so that plus 2, remember, shifting everything up 2. We kind of already said that. The 2 in front of cosine, that's an amplitude. And we also know the negative is going to turn that upside down. And then the 1/2. So if I do 2 pi divided by 1/2, that 1/2 flips up. My new period is now 4 pi. So that'll be my new period that I'll be counting by when I label this. I do want to factor the 1/2 out. And it seems, maybe, just be careful as you factor that fraction. It's kind of awkward. 1/2 x plus something. And then there's the plus 2. And think about, well, what would have been here? Well, there would have been, to get a pi, divide that out, that would have been a 2 pi. So this represents a shift to the left, right here, 2 pi to the left. And so once we get to that point, we'll graph that. But I might want to first concentrate on just the -2 cosine of 1/2 x and then plus 2. Let's just graph that part first. So we'll go ahead and draw our xy axes. Okay, and I know I'm shifting it up 2 units, so I'm going to draw my new line of symmetry up 2 units. I kind of like that. That gives me my new focus. So that's up 2 units. That's y equals 2. And the fact that I have an amplitude of 2 for cosine, then that normally would have started 2 above that, right? Would have been, right, cosine. Remember, cosine would have done this. That's our cosine function, right? But because it's a negative, it's actually going to start flipped over. So my cosine function is going to start 2 below instead of 2 above because of the negative. And again, I would just sort of draw the curve in. You know what the graph should look like. And then go back and say, oh, well, here was a quarter, here was half, here was 3/4, here was the 4/4, right, into the quadrants. And then do the same thing here. Go up and come back down. And, divide that out. I feel like it's like music, right? We're subdividing, right? Subdivide, as you start counting out rhythms. So we know that the lowest point there is 0. And then the highest point here was 4, right? Because we had a shift up 2 units and an amplitude change of 2 units. Now, 4 pi is the new period. So that means out here is 4 pi. And if you divide that by fourths to count, that's like 1 pi, 2 pi, 3 pi, 4 pi. So there's pi, there's 2 pi, there's 3 pi, there's 4 pi. And this would be -4 pi, negative 3 pi, negative 2 pi, and then negative pi. So that would be perfect if that were our only function. But now we need to shift it to the left 2 pi units. And you've already kind of seen this probably, or you already thought about this. Well, shifting it to the left 2 pi units, I mean, like there are multiple ways I could be shifting these, both to the left and the right, to obtain the exact same graph. Like, for example, I'll go back to blue here. So if I'm shifting this to the left 2 pi units, so this start here is now going to be here, right? Everything's going to be shifted to the left 2 units. Let me get that out of this. So that starts now here. And then this intercept is now here. And this height is now here. And the equilibrium is now back here. And the lower part is now there. So look what's happening here. It is actually it's getting us back to what our normal cosine graph is. So that shift to the left 2 and having a negative reflection, they sort of undid themselves and gave us cosine back. And that's going to happen with the trig functions simply because they're periodic in nature, right? They repeat themselves. So eventually you might shift things so far that you get the same graph back, or you reflected it and shifted it and you get the same graph back. And that's okay. So there's multiple ways to represent these curves that repeat themselves over and over and over. Okay. So, that, again, hopefully that makes sense on that example. And then what we're going to do is we'll just kind of do a follow-up after that, kind of as a whole class, to see if those phase shifts make sense. And one thing I will say is that on the phase shifts, I'll make sure that those phase shifts, they should coincide with what you're already counting by, because it just makes sense to do it that way.